Greetings and welcome to the 13th episode of PHS Physics SOS. Today I'm going to be going over the momentum worksheet, which covers chapter 8, I think. Hang on. Guess what? I lied. It's chapter 6. My bad. Anyways, we're going to start with the first problem, which says, examine the graph on the right to determine the kinetic energy of the 2 kilogram object described by the graph after a displacement of 15 meters. Okay, so let me draw this graph, just a quick sketch of this graph. You have force on the y-axis, and at y equals 10, you have a straight line going all the way to the end of the graph, which is at 15 meters. And this is displacement. So part A is asking for the kinetic energy. Now, the way to find kinetic energy is... Now, part A is asking for kinetic energy, and given the information we have, we can calculate the work done during this time period. Now, we know that work is equal to force times distance, so the work done over this interval of distance is going to be equal to 10 newtons, because the force is 10 newtons throughout the entire 15 meters, times the displacement of 15 meters, which is 150 joules. And we know that work is equal to change in kinetic energy. And I don't think it says it, but we have to assume that it starts at the beginning when displacement is 0. We have to assume that the kinetic energy is 0. So work is equal to change in kinetic energy, which is K final minus K initial. We just said K initial was 0, so we can scratch that out. So 150 joules is equal to K final plus 0, so nothing, which is the answer to part A. Now part B says, determine the velocity of the object after 15 meters. Okay, so we know our kinetic energy at 15 meters. It's 150 joules. And we know that kinetic energy is equal to 1/2 mv squared. And if we set that equal to 150 joules, we can solve because they give us the mass. So with a mass of 2 kilograms, you get 1/2 times 2 times v squared equals 150. Divided over, you get these cancel, so you get v squared equals 150. Take the square root, and you get v equals 12.2. Don't forget our units are going to be meters per second. Now part C says, what simple technique did you use to determine the kinetic energy of the object? Why it doesn't ask this as part of part A is beyond me, because part C is basically asking, how did you do part A? And the answer is you used work equals force times distance. So that is your simple technique. Now question 2 is a very similar question, but instead of giving you force with respect to displacement, it gives you force with respect to time. So just to not confuse you, I'm going to redraw the graph. So we have force, again, is 10 for 15 seconds. This is time. And part A says, determine the momentum of the 2 kilogram object described by the graph at the end of the 15 seconds. Okay, so we know that momentum, change in momentum, which is impulse, which is defined with a capital J, is equal to force times time. And again, they've given us a force of 10 newtons through a time interval of 15 seconds, so our impulse, or our change in momentum, over this time interval is going to be equal to 150 newtons, newton meters, or kilograms times meters per second. These are the same units, this is just a different way of writing them. So, and again, similarly to up here where we had to assume that the initial kinetic energy was 0, because that's basically assuming the initial velocity is 0. Same thing here, we're assuming the initial momentum is 0 because we're assuming the initial velocity is 0. They don't give it to you in the problem, which would be nice, but you just assume it. So that means that our delta momentum, which is equal to P final minus P initial, same thing as up here, we're assuming P initial is 0, so 150 Newton meters equals our final momentum at 15 seconds. So that's part A. Now part B is asking, determine the velocity of the object after 15 seconds. Okay, so we know that it has a a momentum at 15 seconds. It has a momentum of 150. I'm going to write the units a little differently to make it easier. Kilograms times meters per second, which is equal to the momentum at that point, which is equal to, it's getting cut off there. So 150 kilograms times meters per second equals mass times velocity at that point. So we know our mass is 2 kilograms again, so 150 equals 2v, divide it out, you get 75 meters per second equals, v. Now part C says, determine the kinetic energy of the object after 15 seconds. Okay, so this is just going to be taking this velocity and plugging it into our kinetic energy formula. So 1/2 mv squared equals k final, which is the kinetic energy at 15 seconds. So 1/2 times 2 kilograms times v squared equals our k final. So that those cancel, and 75 squared is 70 times 80 is 5600 plus 5. Okay, so 5625 joules is equal to your final kinetic energy. And now finally, part D says, what simple technique did you use to determine the momentum of the object? Again, this is kind of stupid, like part C of the first question. It's asking you, how did you do part A? Because part A says determine the momentum, and part D asks you, what did you use to determine the momentum? And okay, well, we already wrote it down. We used the identity that change in momentum is equal to the impulse is equal to force times time. Hang on, let me get a new sheet of paper. Actually, no, we can keep doing these. Part 3 actually really applies to the first two questions. It's kind of analyzing them. It says, it is fair to say that work is a force applied through a distance. In other words, work equals force times distance. While momentum is, and we just define that over here, force times time. So, like the first problem was force versus distance, and you were working with kinetic energy. And the second problem is force versus time, and you're working with momentum. So hopefully that should make sense. And we can just keep going because the next couple are real simple. Question 4 asks, impulse is defined as, and again we've written it here, we used it in part A of the second problem. Impulse is the change in momentum, and it is equal to force times time. Okay, part 5 does need a new piece of paper though, or question 5, sorry, so give me a second. Okay, so question 5, pen right side up, says demonstrate through dimensional analysis that momentum can be determined via P equals mv. Oh boy, what the hell does that mean? So, excuse me, whoops. So question 5 says demonstrate through dimensional analysis that momentum can be determined via P equals mv. Oh boy, what does that mean? Okay, so we know that they're giving us momentum equals mv. We know that, but we have to prove it. And dimensional analysis, they mean basically showing that the units work. That's what dimensions mean. Dimensions are basically units. So another way that we've looked at momentum, or change in momentum rather, is impulse. And change in momentum is obviously going to have the same units of momentum, so we can prove that the change in momentum, if we can prove the units for change in momentum, we can say that those are also the units for momentum, because it's just a change in. The delta doesn't really mean much. So, and we know that impulse, so change in momentum is equal to impulse, which is equal to force times time. And we know that force, so we know that force is equal to ma times time, mat. So change in momentum, and now if we write out all our units, we get kilograms times meters per second squared times second. So again, I just took all these variables and put in their units. So unit for mass is kilograms, unit for acceleration is meters per second squared, and units for time is seconds. So now, we can cancel, let's put these all in one fraction so it's easier to see. Kilograms times meters times seconds. all over second squared. And we can cancel out one of these, so we get kilograms times meters per second. Aha, we recognize that, don't we? This is a mass times meters per second, which is a velocity, and that is how we find momentum. So we have just proved through dimensional analysis that P equals mv. Now, given we kind of cheated and used an identity that already exists, so this isn't technically proving it, but it's good enough for this worksheet. Now, question 6 says, for all collisions and explosions, the total change in momentum is equal to, and this is just a conceptual question, the change in momentum of the entire system is always going to be 0. You can have an object increase its momentum, but for an object to increase its momentum, another object has to decrease its momentum, or decrease its momentum. So, while any given object can change its momentum, the total change in momentum of the system has to be 0. In other words, and on to the next question, it says, the previous statement summarizes what law? So we just said that the change in momentum always has to be 0. This is the conservation of momentum, is the law for number 7. And now question 8 says, there are 2 general types of collisions. Describe each of those types of collisions and fill in the table related to those collisions on the right. Okay, so first we have our elastic collisions, and then we have our inelastic collisions. And first column, it says, is momentum conserved? And for both of them, we should immediately put yes. If anyone ever asks you, is momentum conserved, no matter what the situation is, you will always answer yes, because momentum is always conserved. And then, let's see. Oh, and then the next column is kinetic energy conserved? Now, kinetic energy is conserved in elastic collisions, but not conserved in inelastic collisions. So an elastic collision, by definition, in an elastic collision, kinetic energy has to be conserved. That's what makes it elastic. And realistically, there are no elastic collisions on a macroatomic level. You only see elastic collisions on a subatomic level. But it makes the math and the physics a lot easier, so we deal with elastic collisions in this class. Now, question 9 is another concept question. It says, a firecracker sitting on a shelf explodes, that's a buzzword there, sending several fragments in a variety of directions. What is the net change in momentum? And again, look back at question 6. For all collisions and explosions, the total change in momentum is equal to 0. So question 9 is asking for the net change in momentum, net, total, same difference, so 0. And then it says, what is the sum of the momentum before and after the collision? 0. So this, the first part, the net momentum before the collision, or sorry, the net change in momentum, that's conservation of momentum. Now, the second part of the question, asking what is the sum of the momentum before and after the collision, is also 0. But that is the definition of an explosion. Because, by definition, an explosion is that is the definition of an explosion, because just the pure definition of explosion, and that is just the definition of explosion, because by definition in an explosion, momentum, the starting momentum is 0. Like if you have a bomb, or whatever, if you have a bomb, and it's just sitting there, it has a velocity of 0, so its momentum 0, because momentum is equal to m times v. And it explodes, now it has, each of these little fragments has momentum, but since they're in the opposite direction, and momentum's a vector, when you add them together, you get 0, right back where you started. So that's kind of 2 concepts wrapped up into one. The next question is question 10, which says, the mass of a toy train engine is 150 grams. It travels along a straight section of track with a velocity of negative 0.7 meters per second. What is the momentum of the toy train engine? So let's see, they've given us m is equal to 150 grams, and v is equal to negative 0.7 meters per second. And they want to know momentum. We know, as we've said several times before, that momentum is equal to mass times velocity. And we know our mass. However, they give us our mass in grams. And as we showed up here, and as we've shown in the past, the unit for mass in the SI system, or the standard unit that you want to have in all your equations, is kilograms. And they give us grams. So to get from grams to kilograms, we just divide by 1,000. And then we get 0.150 kilograms. So momentum is equal to 0.150 kilograms, or sorry, the momentum of the train is equal to 0.150 kilograms times negative 0.7 meters per second. And if you multiply that out, you should get negative 105 kilograms times meters per second. Next question is question 11, which says, a child throws a 5.4 kilogram package horizontally from a boat with a speed of 10 meters per second. Calculate the resulting velocity of the boat, assuming it was initially at rest, and then the boy, that it and the boy have a mass of 80 kilograms. Okay, so, well, this may seem like a weird question. From the standpoint of physics, it is an explosion. You have your boat, and the boy throws something off the boat. So the something on the boat is going to be smaller, and if whatever gets thrown off the boat, it has momentum. But since momentum is conserved, the boat has to respond by moving in this direction. So if this thing goes fast and far out, even though it's small and has a high velocity, the boat's going to move a little bit in this direction. And that's just the concept and the intuition behind the problem. And now we're going to do the math behind it. So if we know that here's our boat, and here's our boy, and here's whatever he throws, and it has a velocity of 10 meters per second and a mass of 5.4 kilograms. So it has a momentum, which equals mv, of 54 kilograms times meters per second. I just multiplied these two together. Which means that for the momentum of the system has to be equal to 0. So that means this momentum has to be equal to the change in momentum of the boat. So this is going to be m of the boat times v of the boat. And we know, or the boat boy system. So they give us that the mass of the boat boy system that goes the other direction from the ball, they give you that is 80 kilograms. And we're looking for its velocity. But we know that it's equal to 54, or we know that its momentum is equal to 54 kilograms meters per second. Oh, that's getting cut off, isn't it? Sorry about that. And so you just divide by 54, and you get the velocity of the boat is equal to 0.675 meters per second. But hang on a second. If conceptually we think back to our problem, we have our boat and our object getting thrown off of it. If this object's going this way, we'll call this the positive direction, so it has positive velocity. Now if the boat has to respond by moving in the opposite direction, the boat has to have negative velocity. So that means this number, our 0.675, actually has to be negative, because they give you that the velocity of the ball is positive. So since the boat is going in the opposite direction, it has to have a negative velocity. Hopefully that should make sense. Now question 10, oh no, sorry, I lied. Question 12 says each croquet ball in a set has a mass of 0.50 kilograms. The green ball travels at 10.5 meters per second and strikes a stationary red ball. If the green ball stops moving, A, what is the final velocity of the red ball after the collision, and B, what kind of collision is this, and C, what law did you use to solve the problem? Okay, wow, that's a lot to digest. Let's go back, reread it all, and draw a picture. So each croquet ball in a set has a mass of 0.5 kilograms. So the green ball, it's a little small. The green ball, the green ball travels at 10.5 meters per second. And strikes a stationary red ball. If the green ball stops moving, so this is our before, and this is our after. This is what is the final velocity of the red ball after the collision. So we know that momentum is conserved, so we know that the initial momentum of the green ball has to be equal to the final momentum of the red ball. So m times v of the green ball has to be equal to m times v of the red ball. But it gives to us in the problem that they both have the same mass, so we can just cancel these out. Which means that the velocity of the green ball, 10.5 meters per second, is going to be equal to the final velocity of the red ball. So there's your answer to part A. Now part B says, what kind of collision is this? Now, by definition, this is an elastic collision because one object stays stationary after the collision and the other object keeps moving, which is kind of the fake way of defining it. The real way of defining it is realizing that the kinetic energy is conserved, and if you plug in all the numbers, you can prove that pretty easily, but it's tedious and unnecessary. And if you just know that in a collision exactly like this, where one object comes, hits another, the first object stops, and the second object keeps moving, that is an elastic collision. So, elastic. Now part C says, what law did you use to solve this problem? And the answer is conservation of momentum. Question 13 says, a bowling ball with a mass of 7 kilograms strikes a pin with a mass of 2 kilograms. The pin flies forward with a velocity of 6 meters per second. The ball continues forward with 4 meters per second. What is the original velocity of the ball? What type of collision is? Okay, pictures. Picture time. So we have our ball beforehand, and it has a velocity of, we don't know. And we have our pin, which initially is stationary, and then afterwards we have our ball with a velocity of 4 meters per second, and our pin with a velocity of, well, actually they hit each other, so they should be like contacting, but whatever. And the pin has a velocity of, I'm looking at the wrong problem, 6 meters per second. So it wants to know what the initial velocity of the ball is, and the way we're going to do this is by obviously conservation of momentum. So we know that the momentum after the collision has to be the same as the momentum before the collision, which means P final is equal to P initial. Now we know that our initial momentum is going to be, let's start with our final momentum since it's on the left. So our final momentum is going to be the mass times the velocity of the final velocity of the ball plus mass times the final velocity of the pin. So this is the momentum of the ball plus the momentum of the pin, the final momentum of them. It's going to be equal to the initial momentum of the ball and the pin. So that's going to be m times v initial of the ball which is what we're solving for, this value right here, plus m times v initial of the pin. Now we know that the pin started at rest, meaning it has a velocity of 0, which means it has a momentum of 0, so we can cancel that out. We know that the mass of the ball is 7 kilograms, so we can plug that into all of these. We know that its final velocity is 4 meters per second, so we can go 7 times 4 plus mass of the pin, which is given to us to be 2 kilograms, times the velocity of the pin, which is 6, times, again, the mass of the ball, times its unknown velocity. Now, again, so now this is just algebra. So 4 times 7 is 28, plus 12 equals 7v initial. So 40 equals 7v initial. So 40 over 7 equals v initial, which is equal to, I have it written down here somewhere, 5.7 meters per second. Now part B says, what type of collision is this? And the answer is, it is a partially inelastic collision, because in a perfectly inelastic collision, one object hits another and they stick. In an elastic collision, one object hits another, the other keeps moving. In a partially inelastic collision, one object hits another and they both keep moving. So that's what this is. Also, some kinetic energy is going to be lost if you plug all these numbers in. You will get some loss in kinetic energy. Question 14 says, a 2 kilogram mass moving to the right makes an elastic head-on collision with a 4 kilogram mass moving to the left at 4 meters per second. The 2 kilogram mass reverses direction after the collision and moves at 3 meters per second. The 4 kilogram mass moves 1 meters per second to the left. What is the initial velocity of the 2 kilogram mass? Okay, so first thing we're going to do is draw a picture. This is a 2 kilogram mass moving to the right. So we have 2 kg moving to the right makes an elastic head-on collision with a 4 kilogram mass moving to the left. This is going this way. 4 kilogram mass moving to the left at 4 meters per second. And then it says the 2 kilogram mass reverses direction after the collision and moves at 3 meters per second. The 4 kilogram mass moves 1 meters per second to the left. What is the initial velocity of the 2 kilogram mass? Okay, so 4 kilograms, 1 meter per second to the left. Okay, so again, this is just a conservation of momentum. So this is the initial, this is the final. So we know that the initial momentum has to be equal to the final momentum. And one thing we need to be careful with in this problem is direction. In this case, I'm going to call right positive and left negative. You could do it either way. You just have to be sure to carry it all through to your answer. So the initial momentum is P of the 2 kilogram object plus the momentum of the 4 kilogram object is equal to the final momentum, sorry, it should be initial, is equal to the final momentum of the 2 kilogram object plus the final momentum of the 4 kilogram object. If we plug in all our numbers, we get m times v plus m times v, mv plus mv, yada yada yada. So we get 2 times our unknown velocity plus 4 times negative 4 is equal to, again, this is 2 for the final one, so this, which is going to be 2 times negative 3 plus mv of this one at the final part, which is going to be 4 times negative 1. So we have 2v minus 16 equals negative 6 minus 4. So 2v minus 16 equals negative 10, 2v equals 6, v equals 3 meters per second. And we defined it as positive just so we could do the math right, but this is going to be to the right. Is there a part B? No, there's not. So we are going to move on to question 15. which says a 90 kilogram halfback runs north and is tackled by a 120 kilogram opponent running south at 4 meters per second. The collision is perfectly inelastic. Just after the tackle, both players move at a velocity of 2 meters per second north. Compute the velocity of the 90 kilogram player just before the tackle. Hit my mic there. Sorry about that. Okay. So, again, we're going to draw a picture. So, a 90 kilogram halfback is running north, and we don't know his velocity. And the 120 kilogram opponent is running south at 4 meters per second. Collision is perfectly inelastic. Just after the tackle, both players move at a velocity of 2 meters per second to the north. So now we have this big blob of two players, which weighs 210 kilograms, moving at a velocity of 2 meters per second to the north. So this is before, and this is after. So we know that the initial momentum of the system has to be equal to the final momentum of the system. Initial momentum is momentum of the 90 kilogram guy plus the momentum of the 120 kilogram guy. Are you starting to see a pattern yet? Because it's the same concept through all the problems. It's equal to our final momentum. So we're going to plug all these in. So we've got MV. So we got 90 times our unknown velocity plus 120 kilograms times 4 meters per second equals 210 kilograms, which is their combined masses, times 2. So we get 90 plus, oh crap, I forgot signs. Okay, sorry. So this is, we're going to call north positive, and we're going to call south negative. So this should actually be negative 4. 90V minus 480 equals 420. And when we move this over, we get 90V equals 900. Cancel these out. You get V equals 10 meters per second. And it's positive, meaning that it is north, because that is how we defined it in the problem. Or we defined it in our math, rather. The next question is question 16. Which says a clay ball with a mass of 0.35 kilograms strikes another 0.35 kilogram clay ball at rest, and the two balls stick together. Their final velocity of the balls is 2.1 meters per second north. What was the first ball's initial velocity? Okay, so that's not in view. 16. So starts out with one ball going this way, does it say north? Whatever. We're going to do right and left. So it starts out with one ball going this way, the other ball's rest, and it ends up with both of them stuck together. Both of them stuck together, moving in this direction at 2.1 meters per second. So the initial momentum of ball 1 plus the initial momentum of ball 2 has to be equal to the final momentum, of both of them. So, both of them stuck together, rather. So we know that the initial momentum is ball 2, 0, because it's at rest, so we can cancel that out. Initial momentum of ball 1 is its mass, which is 0.35 kilograms, times its velocity, which is what we're solving for. And we're going to set that equal to m times v, the second of the combined balls, which is 0.7 kilograms times 2.1 meters per second. And when you multiply that out, you get, I don't have this written down. Hang on, let me get a calculator. Calculator required. So 0.7 times 2.1 is going to give us screen glare, 1.47. So 0.35 times our velocity is equal to 1.47. And if we divide that by 0.35, we get 4.2 meters per second. Now you'll notice that this is double this velocity. The reason that it is exactly double this velocity is because this momentum is exactly double this momentum. It's because these two masses are equal, so this mass is exactly double that mass. So conceptually, you could have just jumped to this in one step without doing any of this math, but you probably have to show some work on a quiz for it. And now, okay, on to multiple choice. Question 17 says, if a force is exerted on an object, which statement is true? A large force produces a large change in the object's momentum. I can tell you right now this is wrong, because the answer itself is a very poorly written answer, which is the intent of the answer. It's not any fault of the writer of the worksheet, it's just the intent of the answer. A large force produces a large change in the object's momentum is a completely arbitrary statement. The only way to relate force and momentum is through impulse, which is change in momentum, which is equal to force times time. No matter how big the force is, the time could be like 1 times 10 to the negative 17th seconds, and no matter how big your force is, it's going to be a very tiny change in momentum. So that's an arbitrary statement, so A is wrong. Part B says, a large force produces a large change in the object momentum, only if the force is applied over a very short time interval. Now I just said that. If I have a huge force of like, say, 10 or 1 times 10 to the 10th newtons, which is a massive amount of force, and you apply that for 1 times 10 to the negative 17 seconds, you get a change in momentum of 1 times 10 to the negative 17th kilograms times meters per second, which is like nearly nothing. You wouldn't notice it ever, possibly. So, B is wrong. Now, part C says a small force applied over a long time interval can produce a large change in the object's momentum. Okay, so let's say we have a small force of 1 newton over a very long time interval of 1 times 10 to the 5th seconds. That gives us a net change in momentum of 1 times 10 to the 5th kilograms times meters per second, which is a huge change in momentum, relatively speaking. So that answer looks good so far. Now let's look at part D. A small force produces a large change in the object's momentum. Completely arbitrary. If you have a small force of 1 newton, and it's applied for, let's keep using this tiny little number, if it's applied for 1 times 10 to the negative 17 seconds, it is going to make a change in the object's momentum of 1 times 10 to the negative 17th kilograms meters per second, which is, this should be 7, not negative 17, or negative 7, sorry. I probably miswrote that earlier. And again, this is a tiny change in momentum. So, D is wrong, because it doesn't include a time interval. It doesn't matter what the force is, it matters what the force and the time are together, because that's what the change in momentum is. That's what impulse is. So the answer is C. And I know that was a bit of a long-winded explanation, but multiple choice questions can be kind of tricky on the quizzes, so it helps to, I hope it helps to have a bit more of an extended explanation. The next question is question 18, which is an astronaut with a mass of 70 kilograms is outside capsule when the tether breaks. How about the capsule? Typo on the worksheet. Tisk tisk. Cobb's been teaching for what, 17 years? I wonder if there's a date on this worksheet. I don't think there is. Okay. Anyway, so an astronaut with a mass of 70 kilograms is outside the capsule when the tether line breaks. To return to the capsule, the astronaut throws a 2.0 kilogram wrench away from the capsule at a velocity of 14 meters per second. At what velocity does the astronaut move towards the capsule? Now, this is basically from the standpoint of physics, this is an explosion question, because you have your astronaut and wrench system, beforehand, and they have a net momentum of 0, or a total momentum of 0, because they are not moving. And then afterwards, you have the wrench flying off in this direction, the velocity of 14 meters per second, and the astronaut going backwards with a little bit of velocity towards his capsule. Anyway, back on the topic of physics, the initial momentum is equal to 0, or the sum of the initial momentum. So that means the sum of the final momentum has to be equal to 0, and this is just a little sigma, which means sum. A little math in there for you, or whatever you want to call it. So that means the final momentum of the wrench plus the final momentum of the astronaut has to be equal to 0. So the final momentum of the wrench is equal to the mass of the wrench times the velocity of the wrench, which is 2 times 14, plus the final momentum of the astronaut, which is 70 times a velocity we don't know, is equal to 0. So 70 times v equals negative 28. And if we divide that out, we get our v equals negative 0.4 meters per second. I have a sad, sad announcement to make. I'm out of this beautiful, giant quadrile graph paper. I have to get more. In the meantime, you'll have to deal with the blank stuff. Hope it doesn't hurt your eyes too bad. Or badly. Shame on my grammar. What am I talking about? This is the physics channel. Okay, on to question 19, which you can't bloody see. 19. Let's try that again. Okay. A 0.2 kilogram baseball is pitched with a velocity. Oh my god, someone has messaged me on Skype. Go away. I need to start being more professional and close Skype before I record. Anywho, back to question 19. A 0.2 kilogram baseball is pitched with a velocity of 40 meters per second and then batted to the pitcher with a velocity of 60 meters per second. What is the magnitude of change in the ball's momentum? This means that it starts out here with a velocity of 40 meters per second, and it's coming back. It gets hit back this way with, oh god damn, you can't see that either. Sorry, it starts out this way with a velocity of 40 meters per second. You still can't see that, bloody hell. Okay, and ends up going back this way with a velocity of 60 meters per second. But since it's in the opposite direction, we're going to call it negative. This means that the net change in, oh, I guess, sorry, we have to change the momentum first. So that means its initial momentum is equal to 40 times 0.2, which is 8 kilograms meters per second. And its final momentum is equal to negative 60 times 0.2, which is negative 12 kilograms times meters per second. So the net change in momentum, the delta P, is equal to negative 20 kilograms meters per second. Oh, that's your answer. Okay. That was easy. Now the next question, question 20, says a 60-gram tennis ball moves at the velocity of 12 meters per second. The ball is struck by a racket, causing it to rebound in the opposite direction, speed of 18 meters per second. What is the ball's change in momentum? Okay. Basically the same problem. They just give you different numbers, and they give it to you in grams because they're obnoxious. Okay. So, this way with 12 meters per second. And then this way at 18 meters per second. So the initial momentum is equal to 0.06 times 12, which is equal to 0.72. And the final momentum, oh, and again, this is opposite directions, so this has to be negative, is 0.06 times negative 18, which is negative 1.08. And these are both kilograms meters per second, but I kind of ran out of room. So the difference in these two is going to be your change in momentum. So you take final minus initial, and you get negative 1.80 kilograms meters per second. They need to make a unit for this, because I don't want to write this every time. Okay. The next question, multiple choice, yay, is question 1 on the sample multiple choice, which says a bug flies into the windshield of a car and makes a big gooey splat on the driver's windows. What kind of collision is this? And momental. Okay, well that's not a thing. We've never heard of that. If you've never heard of something on a quiz and you actually read the chapter, it's probably wrong. B, no collision occurs because of the bug's small mass. Wrong. If something hits something else, no matter how small it is, it's a collision. If an electron hits another, or if two protons smash into each other in the Large Hadron Collider, it's a collision. It doesn't matter that they're tiny, and bugs are way astronomically larger than that. And those are collisions. So B is very wrong. Part C, elastic. Part D, or C, elastic. D, inelastic. Reasonable answers. Okay. So, elastic means that one object hits the other object keeps moving, kinetic energy is conserved. Inelastic can be two objects coming at each other and then going together, stuck together, which is what this is. You have your car moving this direction, and you have your bug that splats into the car, and then the car keeps moving. It's like, whatever. So it is an inelastic collision because the bug did not bounce. Think of elastic collisions as bouncy. The bug did not bounce. It just went stick. Good way to think of it. Elastic, bouncy, inelastic, sticky. Now, question 2 on the multiple choice. A bowling ball of mass m with velocity vb strikes a bowling pin of mass m with no initial velocity. After the collision, the bowling pin has a velocity vb prime. Now, I don't know about you guys, but when I first did this, I thought, okay, let's see if you can see this. Let's see if I can get my webcam to focus. See that little thing right there? I just wrote on it. That's wonderful. That little like tick mark is a prime, meaning that this VB at the beginning is not equal to VB prime. Why they didn't pick something like V final or something that makes more sense is beyond me, but whatever. So, after the collision, the bowling ball has a velocity VB prime. In terms of the previously stated variables, define the velocity of the bowling pin after the collision. So this is similar to some problems we've done before. Initially, you have a bowling ball coming at a pin with velocity VB and a mass of m. And then afterwards, you have the bowling ball moving with a mass VB prime and the pin moving at a velocity that is unknown, and it has a mass of lowercase m, I believe. Yes, it does. So, the initial momentum is equal to the final momentum. So this means that m times VB of the ball initially, oh god, you can't see it again. Okay, m times VB of the ball initially is equal to m times VB prime, which is basically the final of the ball, plus the momentum of this thing, the bowling pin words. So mVB minus mVB prime. Okay, now we have the momentum of the bowling pin isolated, which is m times v of the bowling pin. So v of the bowling pin is what we're looking for. And they give us that the m is just lowercase m. So if we go mvb minus mvb prime all over little m, we get, hey, our velocity of the bowling pin. So this nasty mess of letters and primes and grossness and whatever turns out to be C. Woohoo! We got an answer that's on the page. Now, you should be able to... Actually, there's not much you could eliminate here. You could... Never mind. Okay, question 3 on the multiple choice. Out of focus. Okay, question 3 on the multiple choice says, momentum is conserved for elastic collisions, B, explosions, C, inelastic collisions, or D, all the above. And there's a little law called conservation of momentum, so I think we should be able to know that it's D, all the above, because momentum is always conserved. Okay. Question 4 reads, 2 identical bullets are fired from different weapons. One is shot from a very short-barreled pistol, while the other is fired from a long-barreled rifle. Which bullet will exit the barrel with a larger velocity and why? Now, you have to think of this from a physics standpoint and not a firearm standpoint, because there's a lot more that goes into it than that, but we're thinking of it from a very simple physics standpoint. A, the bullet fired from the pistol is faster because a larger force is applied to it. Well, no. We're assuming that the same force is applied to it. We have to assume that the same force is applied to it, but even if the force was larger, but even if the force was larger, it wouldn't matter, because we care not just about force, but also about the time that the force acted on the object. Answer B, the bullet fired from the rifle is faster because a larger force is applied to it. Again, doesn't matter how large the force is. Well, it does, but it matters. It matters how long it was applied and how large the force is. So part A and B would be like incomplete answers, basically. Now, God, I keep saying part, I mean answer. So answer C, the bullet fired from the pistol is faster because the impulse is greater with the shorter time in the barrel. Wrong, backwards, closer, but wrong. You get no points. Do not pass go, do not collect $200. Impulse is only going to be greater when the time is longer, which is what the next answer says. Because we remember that impulse is equal to force times time. So the greater the time, the greater the impulse. If we have a small time, you're going to get less impulse, given that the force is the same. So part D, which is going to be our right answer, woohoo, says the bullet fired from the rifle is faster because the impulse is greater with the longer time in the barrel. So what this is saying is, assuming the force is the same in the pistol and the rifle, which is not true, but we're going to assume that for the sake of this problem. Since the time of the rifle, the time spent in the rifle is going to be greater than the time, you still can't see it, the time spent in the rifle is going to be greater than the time spent in the pistol, and the force is the same, the impulse of the rifle is going to be longer, therefore the change in momentum will be greater, and since momentum is m times v, and we're assuming the mass is the same, the velocity will be greater. Wow, this page is a mess. Hopefully that makes some semblance of sense. Now, question 5 says, a bullet strikes a block of wood sitting on a fence post and becomes embedded in the wood. The momentum of the bullet is A, greater than that of the... Okay. First concept to think about in this problem. Conservation of momentum. Anyways, onward. Part A, or answer A, greater than that of the bullet plus wood combination. Nope. B, less than that of the bullet wood combination. Nope. Dissipated completely. Even worse. And D, equal to the momentum of the bullet plus the wood. Again, they have to be equal because momentum has to be conserved. So the momentum at the beginning has to be equal to the momentum at the end. Has to be equal to. So look for the words equal to in conservation momentum problems. And finally, we are on the last page, and I need a new piece of paper, so give me a second. Okay, question 1 of the free response on the back page says, what is the gravitational potential energy? Oh, nope, sorry, I gotta read the question. A 20-kilogram bullet is fired, a 20-gram bullet is fired from a 1.5 kilogram. Question 1 of the free response on the back page says a 20-gram bullet is fired into a 1.5 kilogram block of wood suspended by a cord. The bullet becomes completely embedded within the block upon impact. The bullet block combination swings as a pendulum up to a height of 0.25 meters. So I'm going to draw this out. No, you don't technically need to. It's going to help. You have your bullet flying towards a block of wood on a string, because apparently people do this all the time because it's in like a million physics problems. So this is your before. This is stationary, so this is not moving. And your bullet, oh, please focus. Thank you. So your bullet is moving, your block is stationary, and afterwards, your block has swung upwards a little bit, and it has the bullet in it, and has swung upwards a distance of 0.25 meters. So, part 1 says, question 1 says, what is the gravitational potential energy of the bullet and block combination at the top of the pendulum swing? Okay, so gravitational potential energy, moving back a chapter, is U sub g, which is equal to m times g times h. Now we have to remember that they're asking about the bullet block combination. So for m, it's going to be the mass of the block, which is 1.5 kilograms, plus the mass of the bullet, which is 20 grams, or 0.02 kilograms, times gravity, which is 9.8, and then times our height, which is the height that this thing swung upwards, which is going to be equal to 0.25 meters, because it's given to you in the problem. And when you multiply those all together, or add these first, then multiply them together, don't forget order of operations, you should get 3.73 joules. So that is the gravitational potential energy that is gained by this block bullet system when it swings upward 0.25 meters. Part 2 says, what was the velocity of the bullet block combination just after impact? So this is asking, right when the bullet hits the block, the system has velocity. So if we remember our energy laws, or not, laws, the law of conservation of energy, you'll know that, we'll recall that the mechanical energy of a system is going to be conserved, which means its potential energy plus its kinetic energy at the beginning is going to be equal to its potential plus its kinetic at the end. So, at the beginning, since this has no gain in height yet, it is all kinetic energy, so no potential. And then at the end, when it's at the top of its, it's at the top of its swing, it has no kinetic energy, it stopped moving for a brief moment in time, it's about to swing back down, it has all potential and no kinetic, because it's briefly stopped moving. And since these two sums are equal, that means we can set the initial kinetic energy equal to the final gravitational potential, which we just calculated. So our initial kinetic energy is equal to 3.73 joules. So 1/2 mv squared equals 3.73 joules. And again, our mass is the mass of the block plus the mass of the bullet. So 1.52 times 1/2 times v squared equals 3.73 joules. Do a little algebra, we get v squared equals 2 times 3.73 over 1.52. I'm writing sideways. So if you take the square root of both sides, you will get that v is equal to, drum roll please, 2.2 meters per second. Sorry, 2.21. Now on to part 3 of this question. It says, what is the momentum of the bullet block combination just after the impact? Aha! So we just calculated the velocity of the bullet block combination just after the impact. We know the mass of the bullet block combination, so we can use that to calculate the momentum, because momentum is just mv. So this is going to be equal to 1.52, which is the mass of the bullet plus the block, times its velocity, which is 2.21, Again, this is the velocity that we just calculated right after impact. And that's going to give you 3.34 kilograms meters per second. Now, question 4. Oh, that's your answer, by the way. Question, or part 4 says, what is the initial velocity of the bullet before the collision? Okay, so now they're testing your knowledge. Now they're testing the knowledge of conservation of momentum, which is that the initial momentum of the bullet is going to be equal to the momentum of the block plus the bullet right after the collision. Which means that this value that we just calculated, which is the momentum of this bullet block combination right after the collision, is going to be equal to the initial momentum of the bullet. So we take 3.34 equals m of the bullet times v of the bullet. So 3.34 equals, and the mass of the bullet is 0.02 grams, or sorry, 0.02 kilograms, 20 grams, times the velocity. So divide that out, 3.34 over 0.02, and you should get 167 meters per second. And this answer should make sense to you, because if you have a small object moving really fast and it hits a larger object and they stick together, then they're going to have same momentum. The sums of their momentum will be the same, but the velocity of that larger system is going to be a lot lower. 167 down to 2.21. Okay, you have made it to the final question of the worksheet, or you just skipped ahead in the video. Either way. Almost done. So, the final free response question says 2 railroad cars are on the same track. Each car has a mass of 10,000 kilograms. Car A has a velocity of 3 meters per second. Car B has a velocity of 1 meter per second. Car A and B are moving in the same direction. They collide simultaneously and are linked together after the collision. So, picture time. A, 3 meters per second. And then B, 1 meter per second. 1 meter per second. And then afterwards we have the total car connectedness moving at an unknown velocity. And question 1 says, what is the total momentum after the collision? So we know that the total momentum after the collision has to be equal to the total momentum before the collision. So P final of the system has to be equal to P initial of the system. Let's quote question 1, by the way. Which means that the final momentum of this plus the initial momentum of these two added together will be the same. So P final equals the initial momentum, so it's going to be momentum of A plus momentum of B. And the final momentum we're going to call momentum of A times B, or A and B, sorry, which is going to be 3 times 10,000, so 30,000, plus momentum of B, which is 1 times 10,000, which is 10,000. You add them together, you get 40,000 kilograms times meters per second. And again, the way I got this was just m times v of car A plus m times v of car 2, or car B, sorry. So this is question 1, and question 2 says, what is the velocity of the link car A, velocity of link car A after collision? So it's asking for the velocity of this part of the combined carness after the collision. And since they're stuck together, the velocity of this part is going to be the same as the velocity of the whole thing. So we just take the total momentum divided by the total mass to get the total velocity, which is going to be the same as the velocity for any given part. So we take 40,000 from here, which is equal to the momentum of this whole mess, divide it by the mass of these two together, which is 20,000, because each has a mass of 10,000 kilograms. And when you divide that, you get 2 meters per second. The final question of this massive 4-page worksheet is, what force was applied to car B if the collision took place over 0.3 meters? And this is kind of a big jump in lots of equalities, but the only way we can relate distance and force is force times distance equals work, which is equal to change in kinetic energy. And since we know the mass and the initial and final velocity, we can calculate the change in kinetic energy, which can be equal to our work, and we know our displacement, we know the distance that the force was applied through, which is 0.3 meters, so we can calculate the force that was applied. So force times 0.3 meters equals change in kinetic energy, and this is for car B, which is equal to K final of car B minus K initial of car B. So initially, or let's start with final first. So K final of car B is 1/2 m, which is 10,000. 1/2 mv squared, and we know that the velocity of the combination of the cars is 2 meters per second. So it's going to be 2 squared. Minus the initial velocity of B, and initially it was moving at 1 meters per second, so that's going to be 1/2 of 10,000 times 1 squared. So it's going to be 20,000 minus 5,000. These are in joules. Is equal to the work done. So that's going to be 15,000 joules equals our unknown force times the 0.3 meters that was applied through. When we divide by 0.3, we get force equals 50,000, and our unit's going to be newtons because it's a force. Woohoo, isn't that a doozy? Okay, so thank you for watching this episode of PHS Physics SOS. I hope you found it useful. I apologize for being in a bit of a goofy mood. It is well past midnight, but I still hope you got something out of this, and maybe even a bit of a giggle or two. Please just, if you have any further questions, just get a hold of me on Facebook or Skype or whatever, and or even in person at school, and I'll do my best to help you. So thanks for watching.